All right, let's start. So the reading for Monday is the rest of that Brower and Curtin paper, that sort of tutorial that actually uses Elm 4. There's a lot of useful tips that we're going to get into in a bit. So finish that up. I wasn't able to find yet, but I wanted one other reading that covers some of the conceptual topics that we'll be going through today, because they're a little bit complicated. So the approach that I'm taking for the rest of this unit is I'm going to go through some of the big picture concepts and some of the complicated details, but there's a lot that goes into what we're going to be talking about linear mixed effects models. There's a lot of readings out there. Actually, this is another of those topics where methodologists are actively working on it right now. So we're still figuring out best practices and a lot of different things related to linear mixed effects models. So I'm going to try to find one that's not too ridiculously technical. Many of you go looking for linear mixed effects models papers. Many of them are kind of impenetrable because they're written for methodologists. But I'll see if I can find one more tutorial that I'll probably post as a supplemental reading for Wednesday and Monday. I already have a reading listed that I'd like you to do by Monday. So that's still a ways off. That's just giving you a heads up that it's already posted, and I think it would help with what we talked about on next Monday and Wednesday.
So there's no homework due this Wednesday?
Sorry?
Is there homework due this week?
Was there not a homework posted?
I don't see anything on that.
I'll have to talk to Austin about that. Well, I'll make a note.
I mean, I didn't mean to put it.
I do definitely want homework for this week. So that was, yeah, I'll see if I can get that straightened out.
I don't stack holding on.
I know he was busy last week, so no worries, but that should be posted. Okay. So this is going to be a new unit that extends some concepts that we talked about in the repeated measures unit. And with this unit, we're still going to be talking about repeated measurement, but I wanted to give this unit a new number because we are getting into a few topics that are new and into a few new statistical concepts that are new to or rather that build on concepts that we've already been talking about, but there is new content here. So to motivate this new unit, we're going to work with a slight variation of the same problem of looking at grade reviews. What's new in this particular data set that we'll start with is we still have 50 people who are evaluating grants of various types. But each person evaluates 4 grants. So they get four different grants to submit reviews for. And the grants have already been reviewed. So they have gone through a whole review process. They have received scores. And we have for each grant the score on that same 1 to 9 scale that the new reviewers are using. So one way to think about what this previous score represents, it's another variable just like quality, high versus low, but it's quantitative. So the scores can range, the previous scores can range from 1 to 9. And because it's different for each grant that the reviewers receive, this is something that varies within reviewers. So quantitative varies within reviewers, and we have 4 observations, 4 cases per reviewer. Outcome is still the same. We're still working with this 1 to 9 scale, 1 being better. So just to give you a sense of what the data set looks like, because we have 4 grant reviews from each reviewer gives us 4 rows in our long data set. So notice reviewer 1 has impact scores, the overall impact, that's the thing that indicates the grants. We also have a number that indicates the previous scores that the grants have received. I'm calling it quality instead of quality dichotomies. So based on the process that we've been using so far, you might think, well, look, we can basically follow that same process where we break apart this data set into separate chunks. We create a little linear model for each of the chunks. So in this case, it would be an intercept plus a slope for quality at second column right here. We do that 50 times because we have 50 reviewers. So we get 50 little miniature data sets. And across those 50 little linear models, 1 per reviewer, we get different parameters, little reviewer intercepts and reviewer slopes. So 1 parameter for each of the parameters in that linear model that we give to each of our reviewers. So here's what that looks like if we go through that process. That gives us sort of like a new data set, a new derived data set that we can work with. That derived data set has a bunch of intercepts and slopes. And then we can go through the second stage where we fit another model on the intercepts and slopes. Yeah.
Sorry, just a quick refresher.
Yeah.
Where is the intercept and slope coming from?
We're treating each of these 50 chunks as if it's its own small data set. So on each of the 50 chunks, we're fitting a little linear model that gives us an intercept and a slope. So it'd be like the mean of all the scores, and then whatever the slope would be if you find the best slope for a given split. So that makes sense.
Mm-hmm.
So it's the same process that we would do with a larger data set, it's just that we're doing it 50 times. This is the same process that we went through last week when we were first thinking about how to deal with repeated measures. So it seems like we ought to be able to do that again. Even though I've changed some things, I've made quality quantitative, I've got more scores per reviewer. Seems like we ought to be able to use this process just fine. Questions? So let's consider 1 reviewer. I'm going to focus in on just one of these 50 subsets of data. This is one of the sets of scores that one of our reviewers gave us. Notice we've got 4 points on the scatter plot. The points are at different points on the x-axis. It's not like we have -1/2 and +1/2, but it looks like any other data set that we work with. By the way, just for convenience, I'm going to be working with centered the centered previous scores, just because it makes a few things a little bit easier as I go through. So here is this reviewer's intercept. That's the gray line. The slope, that's indicated by the black line. Those are just those parameters that I extracted for this reviewer. So it looks like this process is very similar as it was before. One point that I want to draw out of this is that even though I changed from a dichotomous predictor, like quality, minus a half and positive half, to one that's quantitative, where, people can have scores that vary from 1 to 9 on the raw scale. It looks like the same process applies. There's nothing necessarily new about what we're doing. And as we've seen at various points during the course, that's going to be true generally. There's not much of a difference between dichotomous predictors and quantitative predictors. You just go through this same process. So that's one takeaway that we can get so far. It looks like if we have variables that are quantitative and vary within participants, we can treat them basically the same as we would if they were dichotomous and vary within participants. So okay, that's interesting. One thing that does appear to be different, though, if you look at this graph, is that each of these points has some deviation from this regression line that we've had. So notice, we're not perfectly predicting, or we can't perfectly reproduce any of these given observations. There's some error in our estimate for this one participant. So the reason I say that that's different is that when we first started working with these models, when we had, say, 2 points for a given reviewer, and we were extracting out an intercept and a slope, we had as many random effects, as many parameters that we were extracting out from this participant as we have observations from this participant. So if I wanted to, I could use the intercept and the slope that I get for this participant to give me back what their 2 scores were. Whereas if I look at the previous graph here, there's no way I can use the intercept and the slope that I get from this reviewer to perfectly reproduce what this reviewer's scores were. Do people see the difference here? So
Degree of error, prediction error.
There's some prediction error in these little estimates that I'm getting from for each reviewer. So before, there wasn't any prediction error because I had each reviewer gave me 2 estimates plus an intercept and slope. Well, I can just use that intercept and slope to get me back what the estimates are. So there's no error in that participant's parameters. But here there is. So there's no way I can use those 2 numbers, the intercept and the slope, to get me back exactly what these scores are. I can't do it. It's impossible. So that means that the intercept and the slope that I get from this participant are going to be off by some degree, by some amount. There's probably a way to measure by what degree they're off. But big picture idea here, there's some error in my estimates of what's happening with each participant. One thing that I want to point out is that even in a simpler model where I have just 2 estimates for each participant, it still is the case that my estimates of how harsh is this reviewer on average in reviewing the grade centers, or how much do they respond to quality. There still probably is some error in my estimates of what this reviewer is going to be like on those 2 things. It's just that I didn't have the observations to give me an estimate of that error. In essence, it could be that on the day that this reviewer gave me their reviews, they were working in a really noisy coffee shop, and they got pretty annoyed, and therefore they gave more harsh reviews than they would ordinarily. That might be a source of error. But I have no way of knowing that given the data that they gave me. But if I had more estimates, if I had them review more grants, I might be able to get a sense of what that degree of error would be on average. Yeah.
So it's not the fact that these are qualitative variables, it's that you only have two of them, which is why
It's the number. Yeah. It's the number combined with how much information I'm getting on each review.
Gotcha.
So how many parameters am I estimating? So this is really important. It's not like in this design, the error is not present. It is, I just can't estimate it. And that's, of course, generally true about all designs that we work with. Each design gives us the opportunity to estimate different sources of error. In some designs, the error that is there is hidden somewhere. We can't attribute the height of these 2 points to things about the reviewer versus things about the day that they have to submit the reviews. Questions on that? So this is a new idea. With the data set that we're working with, we can sort of see the fact that there's error in the things that we're estimating about each reviewer, whereas in data sets that we worked with previously, that feature was hidden. We couldn't see any sort of error about these individual estimates. So one way of thinking about what it means to make this change is that before that little regression that I was using for each participant did not have an error term. I left it out because we didn't have a way of estimating it. But here, that little regression equation that we're using for each review, we're applying it 50 times, that has a little error term. What that means is that we're able to get some sort of sense of other sources of error besides like how harsh each reviewer is on average or how much they respond to quality. We're able to estimate other sources of error besides those things that might affect reviewer scores. Could also be measurement error. You know, we don't know what exactly is causing it, but it's error. So big picture idea here, our ability to estimate that error has to do with the number of pieces of information we extract out of each reviewer versus the number of observations that we have for each reviewer. The more observations we have for each reviewer, the better we're able to say, like, this is this person's real intercept versus this is other sources of error that don't have to do with the random flex levels.
Sorry, Patrick.
Yeah.
So what was that second point saying there? The number of random effects is less than the number of observations.
Yes. So this is that point that I was just making where if we try to get 5 pieces of information out of each reviewer, we just can't do that. Actually, this doesn't really matter, but there are ways to do that, but it doesn't always work, and it's very precise. So it's not technically true that you can't do it, but in practical terms it is. And the reason this is true, you can think about, last semester I talked about this concept of overfitting, where if you estimate 20 parameters out of 20 points, you're going to be able to perfectly reproduce the raw data points. But your parameter estimates are going to be meaningless. Same idea here.
Can you repeat that one more time?
Yeah. This is sort of related to that idea of overfitting that I talked about last semester. The idea behind overfitting is that, let's say you have 5 data points and you estimate 5 parameters. When you plot your predictions for against your data, what you're going to find is that your model will be able to perfectly reproduce the data that you have. But it's not necessarily going to mean much. It's not going to be a very good model. You get 5 more data points and it's just going to be garbage. So this is a similar idea here. The more information you have from each reviewer, the better able you are to attribute their how they behave to things about them versus other stuff. Questions? Then the other big picture point is that it is always true that you're getting estimates about anything. There's going to be error in those estimates. And one source of error in estimates about reviewers is like their intercept, so how harsh versus lenient they are on average, or their responsiveness to quality. So some reviewers might really respond a lot to different quality grants versus some reviewers might give all the grades that they get the same score. So those sources of error are always there regardless of whether we estimate them. It's just that if we get lots of scores per reviewer, that gives us the opportunity to estimate those different sources of variability. Questions? This is one of the more conceptually deep issues in this unit, so it's worth thinking about. Okay, so we've gone through that process, getting reviewer estimates, and then so that's at stage 1 in this process that I introduced for fitting these kinds of models. In stage 2, we fit an overall model using those like individual reviewer intercepts and slopes. So we might, for example, take the average of the intercepts and the average of the slopes. In this particular example, this is what that model looks like if you fit it in Melbourne. So at the reviewer level, those little reviewer specific models, we've got an intercept, which I haven't shown, but is added by default, and a slope quality. These are called the random effects. And in the second stage, we've got an intercept and a slope quality. Those are called the fixed effects.
Is this the same as last time too? Whenever you have that?
Yeah, this model syntax looks exactly the same. So even though there's something different happening in the model, the way it works in Homer is quite similar. And that is generally true.
Are you always going to have the quality, like the fixed effect variables in the first stage part of the code?
You can leave this out. What would happen if you left it out is that you wouldn't get the average slope for all reviewers. You still be estimating the variability, but you'd be saying it doesn't even make sense to estimate the fixed effect. There's no like common effective quality across reviewers. So you can actually leave different elements of these out, and I will talk about that more on either on Wednesday or on Monday. I'm not sure how long it will take. But for now, we haven't thought about removing any of these components at all. So yeah, the way this looks is should be pretty familiar. Elmer works exactly the same as it does with any other model. So here's the output that you get if you fit this model using Elmer. Let's think about this intercept for a second. So can someone use this intercept as a sentence to describe what it might mean? Remember here, quality is centered. So we've subtracted out the mean from quality before fitting this model.
So I think that's going to be your impact score for average quality.
The average quality grant got an impact score of 3.15. Perfect.
And that's for the whole data set, not for participant.
You could think about it either for the whole data set or per participant. So you could say the average of the impacts of the average of the reviewer level intercepts is 3.15. But here it doesn't really make a difference. It means the same thing. Okay, how about the slope? What do you think this slope means?
So how much it changes between each quality.
Yep, so a 1 unit increase in the past impact scores is associated with a 0.31 unit increase in current impact scores. This one you could think of as operating within reviewer. So within reviewers, people gave grants that varied in past impact scores by 1 unit. A change in quality score of 3.31. So it seems like, thus far anyway, even though we made these changes in design, so we made quality quantitative instead of dichotomous, and we also increased the number of observations that each reviewer gave us. Doesn't seem like much changed. But I do want to highlight something that might be a little bit odd on the screen. That is the degrees of freedom that we get when we get our significance tests. So remember, we have 50 reviewers, but the degrees of freedom that we get out of capital A and ANOVA seem to be fractions, and they're less than 50. So about 48, 49 for the intercept, and about 38 for the slope. That's not something that we've ever seen before. And that's one indication on this screen that the model that we just fit, even though we use the same process, or it seems like we use the same process, actually something different is happening under the hood here. And that is true. And it has to do with this concept that I touched on a little bit earlier, that for each reviewer, we're measuring their intercepts and slopes with a bit of error. The differences between this model and the other models that we've considered has to do with that attribution of error to things about the reviewer versus just random stuff. So for the rest of the lecture, I'm just going to be talking about what's causing these differences and what specifically those differences are. But I want to highlight again that the results that you get out of Elmer can be interpreted in a very similar way as the results that we looked at. And in fact, the procedure that you use in Elmer to get those estimates, it also looks really similar. You know, you even pointed out the formula was exactly the same as we had used before.
Could we go through and interpret the random effects from the previous?
Yes, we will do that. Can I pull off that for just a bit? Okay. Because the random effects they're really what's different about this model versus other models that we consider. Okay, so what I'm showing you here is, remember I made these like multi-panel plots, one for each reviewer. So this is showing our 50 reviewers, along with the review scores that they gave us, those 4 review scores per reviewer. And what I've drawn here is I've placed the blue line that represents each reviewer's individual intercepts. And this is important here. When I say individual intercept, this is something that I'm getting out from LM. So I'm going through that process of dividing up the data set into 50 chunks. I find the intercept and slope for each of the 50 chunks, where the best intercept and slope, the estimate that I actually use, is the one that minimizes the sum of the squared error for that one review. So it's as if I literally made a new data set, used LM on that new data set, and then figured out what the slope, what the intercept is, and I put it on the graph. What I'm going to show you next is the reviewer intercept that I get from Elmer, this new function that we're working with in the scene. You can get the reviewer intercepts using a function called RANF, random effects. And literally what it gives you is some estimates for each reviewer of their whatever parameters you're looking at for each reviewer. And notice, one thing that's a little bit weird is that the intercepts that I get from Elmer are not exactly the same as the ones that we get from LM. So we're doing something slightly different from just literally dividing up the data set into 50 chunks and then, you know, getting a linear model for each person. It used to be that we were doing that, essentially. But something about the way we changed our the design of the study means that we're now doing something slightly different. What I'm going to show you next is I'm going to draw a black line for the fixed effects, where the fixed effects mean, again, our common estimate across people, so like sort of the average of each of these reviewer intercepts and slopes. Okay. Someone tell me, do you notice something interesting about the relationship between the blue lines, the red lines, and black lines?
Seems like they have the same slope.
Well, they all have the same slope because I'm fixing the slope to 0. But yes, that is true. I've removed out the slopes so that we can just look at intercepts on this graph. Anybody notice anything else?
It kind of looks to me like that fixed effects is closer to the red line in most cases.
Yeah, well, let's look through the panels. So here, red line is closer to the black line. Here, same. You got it. It is always the case on this graph that the red lines, things that we get from Elmer, are closer to the black lines, the fixed effects, than are the things that we get from Elmer. It's as if our estimates for each reviewer were shrunk towards the black line. And you can see this very directly, actually, if you create a separate plot for what you get from LM, what you get from Elmer. Notice it's quite noticeable how on this side, the thing that we get from LM, we see more variation in those reviewer intercepts than if we look over here. All the red lines have been shrunk towards that black line. That's quite interesting. Let's go through the same process with the intercepts. So we didn't just get, the slopes. So we didn't just get intercepts for each person. We also got slopes representing how they responded to grants during fall. So the blue lines indicate what would the responsiveness of each reviewer to these grades, so that the slopes that you get from LM. And just a note here, when I've drawn these blue lines, I've made sure that everybody's using common intercept so that we can see the differences in the slopes a little better. Here's what we're getting from Elmer. So sometimes the estimates are the same, but sometimes they're quite different. So notice number 35 up here. And here are the fixed effects. So what do you notice about the relationship between the blue lines, the red lines, the black lines?
The black, red lines are more aligned.
We're seeing the same thing that we saw in the previous graph. It's almost as if each of these slopes was shrunk towards the black line. It moved closer to the black line. The blue lines seem to be really variable. Again, we can notice number 35 up here. But what we actually get out from Elmer is closer to those fixed effects than what we get from Elmer. So there's something really different that's happening here. The reason I say it's different is, like, remember when we were getting as many random effects as we had observations. So one intercept, one slope, two grades. There wasn't really any room to modify these intercepts and slopes, as we were able to perfectly reproduce every efficiency. Here we can't, and something's happened to our estimates where they changed relative to what we might expect, or relative to the procedures that we've used in the past. Questions on that?
You're probably going to go into this, but some sort of like better predictive model using this effects.
There's something that's happening under the hood that might be better under some definition of better. Yes, your intuition is correct. So we're using some sort of procedure that defines better in a different way. I'll get to that in a second, but you're right on.
And I have one further question.
Yeah.
On number 26 there, so, and you may get into this too, but it seems like that blue line is like a better fit.
It's closer to the points, absolutely. So think about when you use LM, what LM does is it minimizes the sum of the squared prediction errors. And we found out that minimizing the sum of the squared prediction errors is one way of getting closest to those points. There's even proof about it. So there's something that Elmer is doing something that's different from what LM does, and it moves some of these lines farther away from the points. And the direction that it moves those individual lines is towards the fixed effects, towards that common slope. yeah, it's a great observation. So just to give you another way of looking at this, here's what we get out of LM. Notice the slopes are all over the place. They're really variable. Here's what we get from Elmer. The slopes are slope-like variable. We still have some that are close to 0 or even negative. But it seems like all the slopes have moved closer to that back black line. They've shrunk towards that black line. So let me see if I could give you an intuition as to why it might be useful to shrink towards the black line.
And the black line represents.
The black line is the common slope, so the slope that we're giving to everybody. It's sort of the average of the slopes.
Is that reflected in the power output?
The amount of shrinkage.
No, the black line.
Oh, yeah, so the black line, this is those horizontal black lines that intersect. Another way of talking about that is fixed effects, which is also labeled on the R output.
What I meant, like the big heavy black line that you were just referring to, like the overall estimate.
Yeah, that's the second line, which is, this is the slope that we're giving for everybody.
Okay.
So yeah, just to be very explicit, when I draw the black lines across each of these panels, the reason the black line is at the same point is that it's literally the same number. It's that 3.15. And on this set of graphs, when I draw this line right here, the reason it looks like it's going in the same direction that has the same slope is because it does. It's the same line that I've drawn 50 times, one for each rear. Is that good? So when I say shrink towards the common estimate, I mean it's shrinking towards, the intercepts are shrinking towards that 3.1415, and the slopes are shrinking towards that 0.3, whatever it was. So, questions?
I'm a little confused. So, like, why are they shrinking? Okay, that's just what I'm not really getting. And like, because don't you get the common estimates from these individual estimates?
Yes, you too. So it looks like we're using the same common estimate, but the individual estimates are different. And there's something weird that's happening to get those individual estimates. Now, I haven't talked about what that is yet, which is what I'm getting to in a little bit.
Okay, I guess that's for me, like, making it hard to pull it together at this point.
So to me, it seems like when you're using this Elmar linear, mixed linear effects modeling, it's sort of taking the individual things for everyone and then kind of shifting their intercepts and slopes to the grand average of all the people.
I mean, I get that. What I don't get is like, why? Yeah, why is that? Like,
Well, let's see if I can answer that, because that's exactly where I'm getting to. Right now, I've just shown you that this is happening, but I haven't provided any sort of justification for it. But let's see why this might be. Let's just assume that the shrinkage is happening. So I'm not going to get into the math behind that. Yeah, I'm not going to talk that much about the math. I'll touch on it. But let's just take it as a given that's happening and think about why it might be a good thing. So, okay, going back to this data set for a second, where I showed you, extracting out these individual intercepts and slopes. Let's focus in on the second person in this data set. So, it looks like this is a change that I made that didn't make its way over to here. I'll just draw it on the board. Let's imagine someone So this is a hypothetical reviewer. And one thing that's noticeable about this reviewer is that they had one score that was really different from the others. That could happen because, random things happen. Maybe when they were reviewing that one grant, they had a baby who was crying in the room, and they just got really annoyed, and so took that out on the grant that they were reviewing. That's that 5, that worse than average score. So random stuff happens over the course of a study. And when you have a small chunk of observations per one person, one of these outlying scores is going to have a big influence on the average intercept and slope that you get for this person. Let's imagine that without that baby crying in the other room, they would have given that grant a 1. Well, suddenly we have a much different, much lower overall average for this person. It's 1.3. Whereas with a 5, it's 4 or whatever. I don't care about the math. It's much higher. And the same thing goes for the slopes, right? So one score that's really different, that's different for random reasons, is going to have a huge influence on the overall intercept and slope that we get for each reviewer. We might want to sort of inoculate our estimates for each reviewer against that possibility, that random variation has a big influence on the estimates that we get for reviewer. That might be better in some way. And we actually have a whole lot of information that could be relevant to this person's intercepts and slopes. Chances are the individual intercept and slope that we get for this reviewer is going to be similar in some ways to the intercepts and slopes that we get for all reviewers. So it might make sense to kind of borrow information that we get from other reviewers because it might be relevant to the information that we get for this reviewer. And that's the sense in which shrinking, so moving our individual estimates for each reviewer towards the common estimate, might be beneficial in some way. In some sense, it inoculates us from getting estimates that are overly influenced by one outline estimate, by random group. We might not have to do this very much if we have a lot of estimates for each reviewer. So if we have, say, 20 estimates for each reviewer, we don't have to worry nearly as much about our individual intercepts and slopes being influenced by random factors. So there are probably situations where it makes sense to do this less, but it might make sense to do this when we have a smaller number of observations per review. Does that make sense? Does that make sense why we might want to do this? So basically, yeah.
So is it so that you're like borrowing information from all the other participants in intercepts and slopes so that if there's one like wonky score, it doesn't overly exert influence on that individual's overall interception?
That's exactly what we're doing.
Patrick, I've got one thing I think probably pieces later. So in that second line, there, to me, it seems to be indicating that when you have less random effects than the number of observations, that increases your error.
Correct. The fewer observations that you have per unit, per reviewer, the more you might want to inoculate your estimates from random fluctuations. But and that ought to make sense because if you have 4 estimates per reviewer, you get a less precise estimate of what that reviewer's overall tendency is to get high versus low scores than if you have 20 or 30 or 40 observations for that one reviewer.
So if you have 20 observations for a participant, 2 random effects, that would decrease your error.
It decreases a type of error, or rather, it gives you more precise estimates of what the error is. The reason that second line is worded the way it is that you can generally only separate these sources of error if you have more observations per reviewer, for example, than you have pieces of information you're taking out from each reviewer. So the intuition here is that if I'm able to, if I can borrow information from other reviewers, that might inoculate my individual estimate from being overly influenced by random fluctuations. And that's one reason why we might want this property of shrinking.
And that's what Elmer does, that LM does it, right?
Yes, we've seen that Elmer does it. I haven't described exactly how that happens. So before I get into how this happens, I'm finally going to talk about the more formal statistical model that we're using. So far I talked about procedures, I haven't posed the sort of formalism, but I haven't introduced it quite yet. But here's the formalism. So in this particular example, we're dealing with a random intercept and a random slope for all. So that's the stuff in orange. And I'm using the letters U, U sub 0, and U sub 1. U just means it's another source of error. We still have this thing out at the edge, this eta that usually meant error when we were dealing with the general linear model. Now we have some other sources of error that are giving other letters just to distinguish them from this type of error. So these are the individual reviewer intercepts and slopes. This is that random fluctuation I was talking about that could influence our estimates of the intercepts and slopes. And then over here, in the second stage, the other half of the model, we've got our intercepts and slopes that are the same for everybody, those fixed effects. So those are the black lines that I showed you on the graphs previously. So this is the formal statistical model. I talked about different pieces of these. What's new today is that because we have more observations per reviewer than we have random effects, we're able to get an estimate of the quantity, which is eta. The sort of reviewer, the factors that don't have anything to do with any individual reviewer, they don't have to do with how an individual reviewer responds to volume manipulation. They're due to maybe crowding in the other room, or the fact that our measure is bad. One quality of this model is that it allows the random effects to borrow information from the fixed effects. So the stuff in orange is shrunk towards the fixed effects. As I've already mentioned, this is a sense in which this model is best, in a different sense of best than we considered previously. So it has something to do not with minimizing the sum of squared errors, but with some other definition of best. There are a couple reasons why or a couple things that will make this shrinkage of estimates towards the fixed effects larger or smaller. There tends to be more of that shrinkage when we don't have a lot of information about each unit. So we have 4 observations instead of 20 per unit. When the units themselves are not very distinct from each other. And what I mean by that is that it isn't the case that reviewer 1 is just generally harsh versus reviewer 2 is generally lenient. So we don't have reviewers that differ in general from each other. Instead, they all tend to give, on average, about the same scores to all the grades. So if they're not very distinct from each other, then it makes more sense to borrow information from our fixed effects.
Why is that? I feel like that's the opposite of what I was.
So let's imagine that we have a case where all our reviewer intercepts close to the black line. If that is true, then it means that there's probably not a lot of new information that we can get from looking at how reviewer 1 is different from reviewer 2. It's probably the case that all the reviewers are about the same. Whereas if we have a case where the reviewers are really different from each other, well, we probably want to look more towards the scores that belong to a given reviewer and less towards the common estimate, because we can get a lot more information from looking at this reviewer's scores than we can from looking at everybody's scores. Does that make sense? Then the last thing that can make shrinkage happen is, to a greater extent, is if there's a lot of observational error. So if there's a lot of observational error, it means that each observation that we get is more distinct from the other observations. So we can gain more from looking at our common estimate across observations than we can at looking at this one review scores. Another quality of shrinkage is that the amount that we're looking at, the fixed effects versus each reviewer's scores, probably ought to have some impact on how many observations we say we have. So if we're saying that each observation is really distinct from each other, maybe it makes more sense to treat them as if they are distinct. But if we're saying that, no, it really matters that this observation is from reviewer 1, then we probably ought to be limited by the number of reviewers that we have, not the number of observations that we have. So here's where the math fits in, because I've described why shrinkage might be attractive and the things that might affect shrinkage, but actually getting the right amount of shrinkage and figuring out, does this part of error belong to how each reviewer is different from each other versus other factors? That's a really difficult problem. And there are a lot of different ways to approach it. So this is where the methodological research comes in, is in how we attribute these different sources of error, and whether we say this is due to stable differences between reviewers versus this is due to just random stuff, random fluctuations. But one thing that is true is that the typical method that we've used of minimizing the sum of squared errors doesn't work very well, because when we minimize the sum of squared errors, we only have one error term. All errors are treated the same. We just look at how each point differs from our predictions, and that's it. We don't go through this process of attributing, this part of the errors due to stated differences between the viewers versus other stuff. That's just not something that we do. One of the most typical ways to do this uses a definition of best that ought to be familiar to you, and that is finding the estimates that maximize the likelihood of observing our data. So we talked about maximum likelihood estimation back when we talked about dichotomous outcomes. That was one of the ways to find the estimates in that case. Well, it comes up here too. And specifically, maximum likelihood is used to find our best estimates of the random effects. That's the thing that makes the attribution of this part of the error belongs to reviewers versus this is just random fluctuations. There are a lot of specific ways to maximize things likelihood. Again, that's something for elders to do. I'm not going to get into the details, but I have provided some readings if you're interested in getting more into the estimates. So that form of maximum likelihood that involves finding the random effects that maximize the likelihood of observing our random effects. That's called restricted maximum likelihood. The reason it's restricted is that it's only applied to the random effects part of our model. Fixed effects we can still find through minimizing the sum of square errors after we've found what those errors are. So going back to our data set, actually, this procedure that we used for the repeated measures part of our last unit, it doesn't quite work here because the estimates that we want that are best in terms of maximizing the likelihood are not these estimates. These are the estimates that are best in terms of minimizing the sum of the square error for each review. So those aren't what we want. They're too variable in this case. We want estimates that are shrunk towards the fixed effects. And that's what maximum likelihood does. So conceptually, what's happening when we use Elmer with this data set is very similar to what we did before. But the implementation, the guts of it, is different. Instead of literally, fitting a little linear model on each, on 50 sections of the data set, we do that, and then we shrink those estimates towards the fixed effects. And that's something that you have to use maximum likelihood. So I've given you the formal model now, and we can see a little bit more how this formal model fits into this null hypothesis significance testing framework that we use throughout the course. So first you have to choose a model. Here's the model that we're using in this case. We've got random effects, and we've got fixed effects. The random effects are part of our error. they're on that error side of the equation. And one thing that's different about a linear mixed effects model is that we have multiple sources of error. We're not treating error as one thing that's, there's no differences between different kinds of error. Instead, we're making some distinctions between different kinds of error. Specifically, we can distinguish between error that's due to features of these units that we're using, so like reviewers or businesses or whatever, and error that's due to everything else.
What's due to what?
Everything else. So everything that's not due to, like, you know, this reviewer is harsher than this other reviewer, or this reviewer responded more to the quality of the information than this other reviewer, all that stuff goes in that data, the overall error terms. And as we've seen, this difference of being able to distinguish between different kinds of error has a lot of implications. It does make this model different from other models that we've considered. Although when you're interpreting those mixed effects, a lot of interpretations feel very similar. Very familiar. Next, you define your null and alternative hypotheses, and you assume the null is true. That gives you compact mathematical models. In your compact model, you're assuming that one of these parameters takes on some value, so like 0. And in your alternative, you're allowing it to take on whatever value that fits best. Next, you have to use some sort of statistic, something to compare your compact Dirac models. And here's another place where the procedure that we're using now is different from other procedures that we've considered before. There are lots of ways to compare models when you're using linear mixed effects models. This is another of those active areas of methodological research. The one that we've been using so far, without me telling you what it is called the Kenworth-Rodger approach. The Kenworth-Rodger approach gives you an F that works very similar to other Fs that you've seen. But one difference is that it gives you fractional values of degrees of freedom. And the reason that does that has to do with what I was saying before about how you're borrowing a lot of strength, or you're shrinking your individual reviewer estimates a lot. That probably means that you ought to say that you have a different amount of information than if you're saying, well, each of these reviewers is really distinct from each other. Once you've compared the models, if the compact and the augmented models are sufficiently different from each other, you can reject the null hypothesis, and you can still do that using the p-value, which you compare to alpha. So a lot of the process is the same, even if the details of how you get there are different. We're working with multiple error terms, and there are different ways to do this model comparison. So going back to the code that we got from R, we now have the tools to understand a few more details about this code. One is what this REML thing means. So REML is short for restricted maximum likelihood. That's saying that we apply maximum likelihood to find the best random effects. And then we do another procedure to find the fixed effects. Restricted means it's just applied to the rating effects. Another thing that we might be able to understand a little bit better is what this control thing is doing. Control is giving special commands to the thing that maximizes the likelihood, that finds the greater values and maximizes the likelihood. Turns out if you're fitting linear mixed effects models, especially if the models get kind of complicated, finding those best rated effects is a little bit challenging. And you often have to do a lot of fiddling to tell the program that maximizes the likelihood how to find those values. I'll get into more of the details of how that works later. That's called trying to get the program to converge. But for now, just letting you know, this is something that's often necessary. Not always, but often. That program that maximizes the likelihood, by the way, it's a special name for it. It's often called the optimizer. These right here are the rating effects, which we've seen before. But one thing that's new in this model is that we now know that these are shrunken towards the fixed effects. That's to protect them from being really crazy due to rating error. Yeah.
Is that why the correlation is 1? If we're shrunk towards fixed effects?
Yeah, I'll talk on Wednesday what that correlation means. 1 usually means that the optimizer couldn't find a good value for it. That correlation right there often doesn't have much influence on interpretation. I haven't put much stock in it, but I will tell you a bit more about what it means on Wednesday. Good question. These values right here is that observational error. So the error due to things that aren't specific to reports. Then we also know why we have to use this other program to find our p-values. Well, that's because there are lots of ways we could have done this. This is a reasonable one. And specifically, the method that it implements is this Kenworth-Roger approach. And finally, we have some sense anyway of why we're getting fractional degrees of freedom here. The Kenworth-Roger approach adjusts those degrees of freedom due to how much its borrowing strength, or the way the effects are borrowing strength from the fixed effects, how much of that shrinkage is occurring. I will talk a little bit more about that concept of how many observations you really have later on. Okay, so this was a pretty heavy lecture because we're changing yet again some of the underpinnings of how our model's working. But I hope you saw some familiar links to other concepts in the past. We're still dealing with those individual reviewer estimates, those individual reviewer slopes. And you can imagine you can get all sorts of different kinds of parameters at the reviewer level or at the level of schools or whatever units you're working in. But what is different is the fact that we're able to separate out error that's due to random variation, reviewer having a bad day or something like that, and error that's due to actual differences between reviewers, one reviewer being harsher on that person. That is it. And in order for, because we're able to separate out those sources of error, another thing that's new is this idea of shrinking towards a common estimate. Again, the reason that happens is if you only have, say, 4 observations per reviewer, those your estimate of how different that reviewer is from other reviewers is going to depend a lot on those four observations. You might want to protect yourself from that random variation. In general, you have more shrinkage when you have not very many observations per unit. So only 4 grants reviewed versus 1. If the units are not very distinct from each other, so the reviewers all give about the same score, it doesn't make sense to look at how one reviewer's scores are different from other reviewers. Or when you have a lot of observation level error. So that being said, it probably makes sense to treat each point as separate. Then the last, really new idea here is this idea of restricted maximum likelihood. So this restricted maximum likelihood is the mechanism that applies a certain amount of shrinkage to your reviewer estimates. That's the way that happens. All right. Well, we'll pick this back up on Wednesday.